Today we're going to be talking about complex numbers. And if you haven't heard of complex numbers before, it's going to be a new number system for you that we'll get to in just a second. But before we talk about complex numbers, the very first thing we're going to do is we're going to review a little bit on how to simplify radicals. Okay? For example here, you know a lot of the perfect squares, like the square root of 9, the square root of 25, and the square root of 49. Okay, when they're all perfect squares, they have nice square roots. So the square root of 9 we know is 3, the square root of 25 is 5, and the square root of 49 is 7. Okay? But what do we do with numbers that are not perfect squares? For example, like the square root of 32. Okay, it's not a perfect square, it's not a nice number. So what we're going to do is we're going to simplify it, kind of like when we simplify fractions. Okay, we always want our fractions to be reduced all the way. We want the same thing to be true with radicals. Okay, now one thing that's going to be extremely helpful for you when you simplify these radicals is your factor sheet that I showed you guys earlier. That's also in the resources in the Google Classroom. And this is really the best time we're going to use these things. So for example here, what if I want to do the square root of 32? How am I going to use the factor sheet to help me with that? Well, the way we're going to simplify radicals is first off, we're going to make factor trees. Okay, and you guys done factor trees before. And if I break apart 32, now 32 has a bunch of different ways we can simplify it that can be simplified. Okay, it can go 8 times 4 is the square root of 32. Or another way I could do 32 is I could do 16 times 2 is 32. Okay, so which way is right? Which way is better? Are we done yet? Okay, a couple of questions. Let's go back to this one on the left here. Okay, if I did 8 and 4, and notice that there's a square root of 8 and the square root of 4. Are either one of those perfect squares? Well, the square root of 4 is a 2, and I call it a big 2. And notice how I X it off and I put a circle around it. Okay, on the left-hand side here, the square root of 8, that's not a perfect square, and it's not simplified enough either. I can simplify 8 into 4 and 2, and the square root of 4 is another big 2. Okay, and this square root of 2, that's as far as I can go there. Okay, so what do I have left here at the end? I have a big 2, another big 2, and the square root of 2. And if I simplify that, I end up with 4 square roots of 2. Okay, so that's one way we can simplify the square root of 32. Okay, a little bit of work there. But this one on the right here, what if I use the two factors 16 and 2? And the way I got these factors is from my factor sheet. If you look up 32, it has the pair 4 and 8 and 16 and 2. Well, watch what happens when I do 16 and 2. If I look at those individually, are either one of those perfect squares? Well, yeah, the square root of 16 is a perfect square. It's a big 4. Okay, notice again how I circled it. The square root of 2 cannot be simplified any further, and I'm done. Look at that. 4 times the square root of 2. And if you look carefully, they're the same answer, aren't they? Okay, now I always ask myself, well, was one of those faster, one of those easier, one of those a little bit shorter than the other one? Yeah, this one, the one on the right, was way shorter. And the reason for that is because we found the biggest number that's a perfect square. And as I alluded to earlier, that's where the factor sheet comes into play. And if you look at 32 on your factor sheet, okay, where's it at here? Right here. You'll notice that the 2 and the 16 are highlighted in black. And there's a lot of these numbers that are highlighted in black. The reason why they're highlighted in black is because those are the biggest perfect square factors. Okay, and those are the ones that you want to use. Okay, so if it has one that's highlighted in black, pick those. Okay, it's going to save yourself a little bit, or ultimately get to the same answer, but it saves us a little bit of work in the long run. Okay, I'm going to take a look at a couple others here real quick. Okay, let's suppose I have the square root of 24. Okay, now 24 is not a perfect square, so it has some factors. And if you look at 24 in your factor sheet, you'll see the two that are highlighted in black are 6 and 4. Okay, and the square root of 4 is 2. Okay, and if I did 6 has a couple factors, 3 and 2. It's the only two factors of 6. But is either one of those a perfect square? No. Okay, so individually, they don't help us very much. So we're going to go back and leave our answer as the square root of 6. 2 square roots of 6. Okay, so we're trying to simplify a radical as much as we possibly can. Okay, if I did another little bit bigger number, how about the square root of 125? And notice when I start my factor trees, there's square roots and square roots. Sometimes people don't put the radical on there, and it messes them up a little bit. The square root of 125, if you look at your factor sheet, it's going to say 25 and 5 are the two that are highlighted in black. And the square root of 25 is 5. And 5 is also a dead end, so it's 5 square roots of 5. Okay? So that's how we're simplifying radicals. I want you to try one by yourself here. I'm going to put up here the square root of 72. Okay? Take 10 seconds here. Push pause and try to find the square root of 72. Okay, welcome back. Let's give it a whirl. If you looked at your factor sheet, the square root of 72, the two that are highlighted in black, are 36 and 2. And the square root of 36 is a perfect square. It's big old 6. And then once again, 2 is done. The answer is 6 square roots of 2. Okay, so just like when we solved equations in the past, when we have fractions as answers, we want our fractions to be simplified all the way. Today we're going to be simplifying and working with some expressions and equations that have radicals in them. And we're always going to want our radicals to be simplified as much as we possibly can. Don't want decimals. We want things left in radical form. Okay? All right, so that's the first thing we're going to take a peek at. Okay, so we simplified some radicals. Okay, and that's kind of what I mentioned here. Simplifying radicals, use the factor sheet as a tool. Okay, now all of these numbers that we looked at so far, I think you've been familiar with. What about the square root of a negative number? Okay, the square root of negative 9. Okay, now what that means is, what number times itself 2 times gives you negative 9? Okay, it has to be the same number. Well, 3 times 3 doesn't work. That's positive 9. Well, how about negative 3 times negative 3? That's also positive 9, not negative 9. So it doesn't work, does it? Okay, so what we have going on next here is this thing called a complex number. It's called an imaginary number. Okay, and it's going to talk about this letter. We're going to talk about this letter I, the imaginary number I. Okay, what I stands for is the square root of negative 1. Okay, and watch what happens here. I can replace the square root of negative 9 as the square root of negative 1 times the square root of 9. Okay, I can separate, and negative 9 is just negative 1 times 9. Okay, the square root of negative 1 turns into an I, and the square root of 9 is 3, and I end up with my answer, 3i. Huh. Okay, so really, all this really means is when I have a negative number under a radical, I'm going to have an I in my answer. Oops, I'm going to have an I in my answer. Okay, and there's kind of how and why it works. Okay, so I'm going to try and simplify a couple of them here once. Okay, how about the square root of negative 18? Now 18 is not a perfect square, but if I simplify it, if I use my factor sheet just like we did a minute ago, if I look at the factor sheet, the two that are highlighted in black are 9 and 2. The square root of 9 is 3, and the square root of 2, so I get 3 square roots of 2. But because it had a negative in there, it's going to have an I in its answer. And that's where we write it typically, is between the coefficient, the big number, and the radical. It kind of goes in the middle. So 3i with the square root of 2. Okay. Here's another one. How about the square root of negative 20? 20 is not a perfect square. Okay. If you look at your factor sheet, 5 and 4 are the two that are highlighted in black. The square root of 4 is 2. Square root of 5 is a dead end. I end up with 2 square roots of 5, and because there was a negative, I have an I in my answer. Okay, so it's not anything a whole lot different. Okay, if I try one more here, how about the square root of negative 45? Okay, 45, if you look at your factor sheet, the two that are highlighted are 9 and 5. Square root of 9 is 3. The square root of 5 is a dead end, and I end up with 3 square roots of 5, but because it's negative, there's an I in my answer. Okay, so this imaginary number I isn't anything to be real scared about, worried about. It just allows us to take the square roots of negative numbers. Okay, and again, this is what's part of what's called the imaginary number system. All the numbers you've learned about so far have been a part of the real number system. Well, now we have these ones called the complex numbers or the imaginary numbers. Okay? All right, well, next up here, let's try to solve some equations. Let's do a little bit of algebra and see if we can solve some equations and see what we get here. So here's the first one. What if I had x squared plus 36 equals 0? Now when it says to solve there, our goal is to get x by itself on one side. Okay, let's try it. Well, here's my x term. I'm going to subtract 36. and I get x squared equals negative 36. Okay, well, we're getting close. We got the x term by itself, but I want to get rid of the square. The way I get rid of a square is I square root. Okay? And when I square root that, the square root cancels out the square, and I just get plain old x. And on the right-hand side, I have the square root of negative 36. Okay? Well, the square root of 36 is 6, but because it's negative 36, it's going to have an I in it. So my answer is 6i. Okay? Now, technically, when I do this, when I do the square root of something, I get two answers. I get plus and minus 6i. Okay? Where that is coming from is, when I take the square root of 36, what number times itself is 36? Well, 6 times 6 is 36. And so is negative 6 and negative 6. So whenever we do the square root, and this is going to come into play a little later here, whenever we do the square root of both sides to solve an equation, we always introduce this plus and the minus, because there's two possible answers. Okay, and we're going to focus on that a little bit more later this chapter. Okay, if I did another one here real quick, how about a second one? How about 5x squared plus 20 equals 0? Okay, a little bit fancier equation. Well, let's get the x by itself. There it is. 20 doesn't have an x in it. So I'm going to subtract it to the other side and make it be negative 20. Divide by 5. And negative 20 divided by 5 is negative 4. So we want to get it down to that x squared term. And then just like we did over there, to get rid of that x squared, we're going to cancel it by square rooting. And there's my I get plain old x. Whenever I square root both sides of an equation, I get a plus or minus. The square root of 4 is 2, and because it's negative, it's going to have an I in it. Okay? So that's how we're going to solve quadratic equations. Okay? I got one last one I want to try here. And again, this one's just a little bit different. How about this one? 6x squared plus 108 equals 0. Okay, doesn't look any different, but let's see what happens here. If I want to get the x squared by itself, I'm going to subtract 108. And I'm going to get negative 108. I'm going to divide by 6. Okay, and if you take 108 divided by 6, you're going to get negative 18. Okay, well, let's do what I did before. I'm going to square root both sides. I'm going to go over here. I get x squared equals plus or minus the square root of negative 18. You know, bad news. Is 18 a perfect square? It's not a perfect square. Okay, so can we simplify it like we did earlier here? Sure. Let's take 18. If I look at my factor sheet, the two that are highlighted in black are 9 and 2. The square root of 9 is 3. That's a dead end, that's a dead end. And what I end up with here is I get, my plus or minus is still there, but I have a 3 square roots of 2. But because it was negative 18, there's going to be an I in my answer. Okay? So it's just solving equations like we have in the past. But whenever we square root, you're going to get two answers, a plus and a minus. And if we're taking the square root of a negative number, we're going to have an I in it. Okay? All right, very good. Okay? So a little bit on simplifying radicals, positive radicals, negative radicals, and then solving some equations that have the letter I in them. Okay? Next item up for bits here is we're going to talk about simplifying expressions that have i's in them using adding and subtracting. And this isn't too bad. If I had 4i plus 2i, with adding and subtracting, the i's act just like x's and y's. X's and y's, they're like terms. 4i plus 2i is going to be 6i. Just like 4x plus 2x is 6x. Okay? How about negative 3i minus 5i? They're like terms. Negative 3 minus 5 is negative 8i. Okay, nothing fancy about that at all. But we're just going to combine like terms. Okay? Now, if I take this a little step further here, these complex expressions really are made up of these imaginary numbers have complex expressions that are made up of two parts. Okay? And sometimes there's a complex number. And a complex number has two parts to it, like I said. It has a real number part. And then this part here is called the imaginary part. Okay, Okay, and how can you tell the difference? Well, the imaginary part has the I in it, the imaginary number in it. Okay, if I have a couple expressions, complex expression, maybe it's like this, 3 plus 5i plus 2 plus 4i. Okay, so I have one complex expression added to another complex number expression. If I combine them together, we're just going to combine like terms again. So if I add the real number parts together, that's the 3 and the 2. 3 plus 2 gives me 5. And then if I add the imaginary parts together, 5i plus 4i is 9i. And there's my answer. And notice they can't be combined together because that doesn't have an I in it. But we just add the real parts with real parts, the imaginary parts with the imaginary parts. Okay, we can do the same thing with subtraction. 3 minus 2i minus 4 plus 5, 4 minus 5i. Okay, well, what if I combine my real parts? That's the 3 and the 4. Now be careful of that subtraction sign. Just like you've always seen in the past here, this subtraction sign changes the sign and everything back here. So it's 3 minus 4, which is negative 1. Those two go together. And then if I combine my imaginary parts, that's these. It's negative 2 minus negative 5. Okay? Negative 2 minus negative 5 we know is a change. And negative 2 plus 5 turns into a positive 3i. Okay, so just be cautious of those with the subtraction ones. You'll see some changes going on there. But ultimately, again, this really comes down to combining like terms. Okay, so adding and subtracting isn't, I don't think, too terribly bad. Okay, next item up for bids here is, how about multiplying complex numbers? Okay, now before we get to that, I need to do a little refresher here. What if I had the square, let's multiply some radicals. The square root of 2 times the square root of 2. A lot of you are going to say that that's the square root of 4, and we know that the square root of 4 is 2. Okay, watch this. The square root of 5 times the square root of 5 is the square root of 25, which is 5. Some of you, I'm hoping you see a little pattern here. How about one more here? The square root of 7 times the square root of 7 is the square root of 49, and the square root of 49 is 7. Okay? Are you guys seeing any relationships between this one and multiplying the same thing together, the same radical together? And I get a big 2. The square root of 5 times the square root of 5 is a big 5. 7 and 7 is a big 7. Okay? There's a nice little relationship with that. Okay? I'm going to try to get you to use that little shortcut and eliminate this middle step. Okay? What if I had this? The square root of 9 times the square root of 9. Don't think the square root of 81, but it's big 9. Okay? The square root of 76 times the square root of 76 is 76. Okay? But anytime we have two radicals that are the same that we're multiplying together, we get that number. And to kind of generalize it, the square root of a times the square root of a is a. Okay? It's just whatever the number is underneath the radical. Okay? Well, can we tie this into these imaginary numbers? Okay? I said that I was equal to the square root of negative 1. Okay? Well, what if I had I squared, which means I times I? What if I multiply, and this is the key here, what if I multiply two i's together? Well, that's the square root of negative 1 times the square root of negative 1. And if I have two negative 1's being multiplied together, the answer is negative 1. So I squared equals negative 1. Okay? And to kind of summarize that, just another way of writing this, I guess, would be, anytime I multiply two i's together, I'm going to get negative 1. And whether you think about it as I squared, or does every two i's make a negative 1, either one is perfectly fine. Okay? Let's take a look at this. What if I had 3i times 2i? Okay? If I multiply by big numbers, I get 6. And then I times I is I squared. Well, if you remember, I squared is the same as negative 1. And my answer would end up being negative 6. Okay? It's kind of showing how to do it there. Okay? How about this one? 4i times 5i. Okay, here's kind of maybe a little bit shorter way to think about it. What I do is I multiply the big numbers together, 4 times 5, and it looks like positive 20. But anytime I have two i's being multiplied together, I times I is negative 1. And negative 1 times 20 makes the answer become negative 20. Okay? How about one last one here? What if I had negative 3i times 4i? If I multiply my big numbers together, to me it looks like negative 3 times 4 is negative 12. But I have a couple i's here. I times I is negative 1. And negative 12 times negative 1 is positive 12. It changes the sign. So anytime we see two i's again, it changes the sign. Sometimes it makes it negative, sometimes it makes the answer positive. Just depends upon kind of what we have here. Okay? I want you to try these two by yourself. 3i times 6i and negative 4i times negative 2i. Okay, so take 30 seconds here, push pause, try them, and then unpause. Ready, set, go. Okay, welcome back. Let's try this. When I look at the first one, 3 times 6 is 18. I times I is negative 1. And negative 1 times 18 is negative 18. It should be a negative. Okay? When I look down here, negative 4 times negative 2, that's a positive 8. A negative times a negative is a positive. And then an I times I is negative 1. So it turns my answer into negative 8. Changes the sign. Okay? All right, so we're going to take this a step further with multiplying i's. Let's try this. Okay? What if I had this? Well, what's I to the 5th power? I to the 5th power. Okay? Well, this can be a little tricky. I to the 5th power is 5 i's. I times I times I 5 times. Okay? And what I want to do is I want to think of this in terms of groups of 2. Okay? I times I, 2 of them, that turns into negative 1. These 2 turn into negative 1. And then I have a little I left over. Okay? So negative 1 times negative 1 is positive 1 with an I. And that means my answer is just one I or just I. You know, like I said, this can be a little tricky. The whole key to it is how many groups of 2 are there? And if I think about this, how many groups of 2 go into 5? Okay? There's 2 groups of 2. Or 2 goes into 5 2 times, which gives me 2 negative 1s, which make a positive 1 with an I left over. Okay, but drawing them out to start with is going to be a little bit helpful. Okay, this is a little confusing. Let me do another one here. How about I to the 11th power? Oh, let's do I to the 7th. There's 7 of them. And remember, every 2 turn into a negative 1. So if I kind of group them together, that turns into negative 1. That turns into negative 1. Those 2 turn into negative 1. And then there's this little guy left over. Well, let's do this. An odd number of negative 1s, negative 1 times negative 1 times negative 1, an odd number of times is going to leave us with negative 1. And then this extra 1 just comes along for the ride. Okay? And negative 1 times I is negative I, is what we're left with. Okay? What if I had an even number of i's? Let's suppose I had this. I to the 6th power. Okay? Well, these 2 make negative 1. Those 2 make negative 1. And those 2 make negative 1. Okay? 2 goes into 6 3 times. There's 3 negative 1s. And an odd number of negative 1s multiplied together is negative 1. And are there any i's left over? No, they all matched up. They all had partners. So my answer is just negative 1. Okay? Okay? And for me, like I said, a lot of times it helps to write them out a little bit. Well, you're going to see a couple problems where the power gets to be pretty big. Okay, what if I had I to the 24th power? Oofta. Okay, now, yep, we can start writing them out here. I times I times I times I. And we could write out 24 of them, but that's too much work. Well, let's think about this. What we're looking for is we're looking for groups of 2. Okay? There's a -1. There's a -1. How many groups of 2 are there in 24? And how many pairs go into 24? Well, 24 divided by 2 would be 12. I would have 12 -1s. And again, I could write them all out. But my point here is I have an even number of negatives. -1s, actually. And if I have an even number, remember every pair turns into a +1. A +1. These next 2 turn into a +1. And if I have a bunch of +1s multiplied together, my answer is just going to be +1. Okay, so we can think about that. How many groups of 2 go into the exponent, and every 2 turn into a positive? Okay, let's try another one here. Again, this is a little confusing. What if I had I to the 41st power? Holy mackerel. Okay, now we're not going to write out 41 i's. Okay, sometimes I write out a couple. And remember, these 2 turn into -1, there's -1, -1, -1. How many groups of 2 would I have in 41? Well, 2 doesn't go into 41 evenly, but 2 goes into 40. Okay, I could have 40 i's, and if I divided them into groups of 2, I would have 20 -1s, and I would have an even number of -1s. And just like we said before, an even number, every 2 turn into a positive. So up to those first 40 i's, I'm going to have a bunch of +1s multiplied together. I'd have 20 of them multiplied together. And then I would have my 41st I. So my answer would just be +I, or 1I, or just I. Okay, this is tricky, and it gets students every year trying to get these. Okay, I'm going to do one last one here. Okay, what if I had I to the 99th power? Let's try that. I to the 99th power. Okay. All right, so obviously we'd be here a long time if we wrote them all out. Okay, but I want to know how many groups of 2 go into 99. Well, 99 doesn't divide by 2 evenly, so I have to go down 1. So what if I think about the first 98 of them? How many groups of 2 would be in 98? Well, 98 divided by 2 is 49. I'd have 49 -1s being multiplied together. That's an odd number of -1s. And an odd number of -1, so -1 times -1 times -1, an odd number of times, is going to leave you with a -1 left over. Okay, just a -1. And then that got me to 98. Well, then I would have my 99th I. So this time it would be a -1I, or just -I. Okay? So again, I think writing it out in groups of 2 is extremely helpful. Okay? But you're going to see a couple problems like that. Okay, oops. One other thing we're going to see with multiplying complex numbers, this is going to be a little bit simpler for us, excuse me, is how about using the distributive property? Okay, this looks more like the real part and the imaginary part when we did adding and subtracting. Well, I can do the same thing with multiplying. What if I distribute? Just like we've always distributed. 5 times 2 is 10i. Now look at this last part. 5 times -3. To me it looks like it should be -15. Okay? But I times I, remember, is -1. And -1 times that makes it become +15. It changes the sign. Okay? We can't combine those because they're not like terms. The 15 doesn't have an I in it. There's my answer. Okay. Watch this. What about 2i times 6 plus 5i? How about this? If I distribute here, okay, I get 12i. 6 times 2 is 12. And then I look at the second part, 2 times 5. To me, it looks like it's positive 10. A positive 2 times a positive 5. But I times I means it's going to multiply by negative 1. And 10 times negative 1 means it's minus 10. It changes the sign. Okay? Let's take this one step further. Okay? Oops. Shoot. Let's take this one step further. Okay? Can we FOIL using complex numbers? 3 plus 2i times 4 minus 5i. We sure can. We can FOIL. Just like we normally would FOIL. Let's start with the 3 and distribute it to both. 3 times 4 is 12. Oops. And then 3 times negative 5 is negative 15i, or minus 15i. If I go to my inside term, I'm going to go to this one and FOIL it. 2 times 4 is 8i. And now this last one is where we have to be really careful. 2 times negative 5, to me it looks like negative 10. But I times I turns into negative 1. And negative 10 times negative 1 makes it become positive 10. And normally I usually don't even write this negative 1 there. Okay? I look at it as negative 10, the I and the I make it become positive 10. And then we go back and combine like terms. If I combine my real parts, 12 plus 10 is 22. And if I combine these parts, negative 15 plus 8 is negative 7i. And there's my answer there. Okay? So we're going to do some FOILing here with i's in these complex numbers as well. Okay, let's try one more FOIL one. Can you try one by yourself here once? I think we're getting the hang of it. How about this one? Negative 3 minus 2i. Negative 4 plus 2i. Let's do that way. So let's push pause, take a second, give it a whirl, and unpause when you're done. Okay? All right, let's give this a try. If I FOIL, negative 3 times negative 4 is positive 12. Negative 3 times 2 is negative 6i. No, now be careful. Negative 2 times negative 4, it looks like positive 8i. Negative 2, positive 8. And how about the last one here? Negative 2 times 2, it looks like negative 4. But I have an I times an I, so it's going to change the sign and make it become positive 4. Okay? If I combine my like terms, the real part, 12 plus 4 is 16. These two, negative 6 plus 8 is 2i. Okay? Right, there we have it. There's multiplying with complex numbers and multiplying with this letter I. One last thing today. Toss it in here. We're going to divide complex numbers. Okay, I'm going to get to the i's and the complex numbers here in just a second. I want you to remember, I think you remember how to do this. What if I had 5 over the square root of 2? Okay, once upon a time when you did some things with radicals, we came across a rule that says we can't have radicals in the bottom. Okay, so we need to do what was called rationalizing the denominator. We need to get rid of that square root of 2 down there in the bottom. And the way we did it is we multiplied by the square root of 2 over the square root of 2. We multiplied the top and the bottom by that radical. Okay? And if I did that, my numerator just multiplies straight across. I get 5 square roots of 2. And my denominator, the square root of 2 times the square root of 2, if you remember that from before, it's 2 of the same radicals, and I multiply them together, it turns into a big 2. Okay? And then I would look at this to see if anything can be simplified. If you can simplify something, it's going to be a big number with a big number out in front. Nothing happens in this case. Let me do one more here. What if I had this? 4 square roots of 3 over 5 square roots of 2. What if it was a little bit fancier problem? Okay. Well, it's okay to have the 2 down here. I'm sorry, it's okay to have the 5, but I can't have the 2. So I'm going to multiply by the square root of 2 over the square root of 2. Okay? And if I look at my numerator, the radical parts I can multiply together. That's 4 square roots of 6. And the bottom, the square root of 2 and the square root of 2, those turn into a big 2. And 2 times 5, I get a 10. Okay? Now the question is, can that be simplified at all? Okay, if I look at the big numbers out in front, I think 2 goes into both of those. And if I divide them both by 2, I get a 2 and I get a 5. And I end up with 2 square roots of 6 over 5. Okay, now my whole point is, how do we get rid of a radical in the bottom? We multiply the top and the bottom by that radical. Okay, well, what do we have, or what do we do rather? Instead of having a radical in the bottom, what if I had this? 3 over 2i. Well, I is just a radical. I is the square root of negative 1. Are we allowed to have i's in the bottom? No, we're not. So to get rid of it, we're going to do the same thing. I'm just going to multiply by I over I. The 2 is okay, but we can't have the I. Okay? So if I do that, I end up with 3i on the top. What does the bottom turn into? Remember, I times I is a negative 1. And negative 1 times 2 is negative 2. Okay? And it's okay to leave your answer like that, but normally we don't leave negative signs in the bottom of a fraction. We bump them up to the top. So this is maybe a little better form of the answer. Negative 3i over 2. Okay, but once again, the way we get rid of that radical in the bottom is we just multiply the top and the bottom by that radical. Okay, here's another one. Let me try another one of these real quick. What if I had 4i plus 2 over 3i? What if I had that? Okay, now the 3's okay down there, but I can't have an I on the bottom. I on the top is okay, but not on the bottom. Oops. So I'm going to multiply by I over I. And this turns into parentheses, and we're going to have to distribute going backwards. Okay, so what about 4i times I? Well, I times I is negative 1, and negative 1 times 4, that turns into negative 4. And the second part is plus 2i. Down on the bottom, I times I, these two turn into negative 1, and 3 times negative 1 is negative 3. Okay? Can anything cancel? Is there anything that can go into 4, 2, and 3? Nope, it can't. But once again, that's okay to leave your answer like that, but it's better to move this negative sign up to the top. And if I moved it up to the top, it makes the 4 become positive 4. It turns it into minus 2i, and I'm left with a positive 3. Okay, very good. Okay, and I'm going to elaborate on this just for 1 second. What if I did a problem and I got an answer that was 12 plus 5i, 12 plus 4i over 6. Can that be reduced? Okay, yes it can, as long as something can be divided into all 3 of those. And if I look carefully, I think 2 goes into all of those numbers. So I could do a 6, divide by 2, divide by 2, I get that. And I would end up with 6 plus 2i over 3. So every once in a great while, we're going to have something that can divide into all 3 of them, but it has to go into all 3 of them. Okay? If I look at this one, some people want to cancel 6 and 3. You can't do it if it only goes into 2. It has to go into all 3 of them. So always make sure you check your answer to see if it can be simplified one step further. Okay? All right, I got one last one here. Type of problem that we're going to see. What if I had 5 over 3 plus 2i? What if I had that down there in the denominator? Okay? Now, it's different than the last ones we saw because it's not just the 2i, there's 2 terms down here. Okay, and when you did radicals a long time ago, the way I got rid of this radical in the bottom is I multiplied the top and the bottom by this thing called the conjugate. Okay, and the conjugate of the denominator, it's the same numbers, but just a different sign. Instead of 3 plus 2i, it's 3 minus 2i. Okay, and we're going to FOIL, and we'll see something that happens here. So this kind of is in parentheses. That's all grouped together, and that's all grouped together. So I'm going to try to distribute the 5 through on the top. Okay, and if I do that, I get 15 minus 10i when I distribute through. Now watch what happens here in the bottom. 3 times 3 is 9. I get minus 6i. When I go to this one, I get plus 6i. And be really, really careful here on the back end. 2 times negative 2, it looks like it's negative 4. But I times I makes it become positive 4 because of the negative 1. Okay, and even more specifically, look what happens here. What happens with the two middle terms with the conjugate? Negative 6i and positive 6i, they're always going to cancel out. And they end up with 9 plus 4 is 13. And that's what I get for an answer right there. Okay, and nothing can go into 15, 10, and 13. So that's my final answer. But what I'm pointing out here is with the conjugate, these middle terms are always going to go away. So really, all you really need to multiply with these is the two first terms and the two last terms. Okay, because those middle ones are going to go away. Okay, we're trying another conjugate problem here. How about this guy? Let's try one more here. How about, oops, sorry. 3i over 4 minus 5i. Okay, well, I see addition or subtraction in the bottom down there, so I'm going to multiply by the conjugate, which in this case is going to be 4 plus 5i. Okay, let's see what I get here. If I distribute, 4 times 3 is 12i. And the second part here, now be careful, 3 times 5 is 15. Looks like positive 15, but they each have an I, so it makes it become negative 15. When I go to the denominator, and I do my conjugates down here, my FOIL, 4 times 4 is 16. I know that that's 20i minus 20i. Those middle ones are going to cancel out, so I'm not even going to write it down. And let's look at the last ones. It looks like negative 5 times negative 5 is negative 25, but the I and the I makes it become positive 25. And if I add those together, 16 plus 25 is 41. Okay? And I look closely at 12, 15, and 41, and I don't think there's anything that goes into all three of them. And there we have it. Okay? All right, here's the very, very last one for us. Okay, this is the fanciest type of problem you're going to see. What if I had this 5 plus 3i over 4 minus 2i? Okay, this is the fanciest one. The numerator and the denominator both have i's in it. They both have addition or subtraction in it. Let's think about what that conjugate would be. And again, we're just going to look at the denominator. If it says 4 minus 2i, the conjugate's going to be 4 plus 2i. And I'm going to multiply all these things together. Holy mackerel, it's going to be one great big FOIL problem. Okay, maybe I'll put it up here. Okay, so I'm going to go 20. Then I'm going to get plus 10i plus 12i. And my last terms here, 3 times 2, it looks like positive 6. But I times I makes it become negative 6. Okay? And maybe I'll keep going here for a second. If I simplify my numerator, 20 minus 6 is 14. 10i plus 12i is 22i. Okay, so there's my numerator. Okay, the denominator goes a little bit faster. 4 times 4 is 16. We know that the outer terms and the inner terms cancel out. They go to 0. So let's look at the last terms. Negative 2 times positive 2 looks like negative 4, but the two i's make it become positive 4. And again, with the conjugate down there, all the i's should go away. We don't have any i's in the denominator anymore. And 16 plus 4 is 20. Okay? Let's look at this answer right here. Can anything go into all three of my big numbers? If you look closely, I think 2 can go into all of them. So if I divide everything by 2, I get a 7, an 11, and a 10. And there's my final answer staring at me here. 7 plus 11i all over 10. Okay? Oh, so there's a lot of stuff here today with this imaginary number I. Okay? But as I tell students in the past year, that let's not make it harder than it has to be. If you can think of I as just a regular variable, an x, a y, an a, and a b, when we're adding and subtracting them, they're exactly the same. Okay? And really they're just combining like terms. And really the main thing that you really have to kind of keep track of and stay focused on is that any time I multiply two i's together, it turns into a negative 1. I times I is negative 1. It changes the sign on the number, and that's the big thing. All right, there we have it, something new. Good luck.